Okay, welcome everybody. Um, Thank you for being here this morning. Thank you for taking the pre-lab quiz. Highly, highly appreciated. We're gonna go ahead and talk today about the details of infrared spectroscopy. So your pre-lab quiz question was, what does IR stand for? It's infrared spectroscopy. Specifically, IR means infrared. Um, we usually say IR to mean the whole spectroscopy, but really it's just infrared, but it's IR spectroscopy, or you can just say IR. So you'll hear people say, we did IR on the molecule. That means we did an infrared spectroscopy analysis. So infrared spectroscopy. Remember, I spoke to you guys about the electromagnetic spectrum. We have two sensors that we were born with in our eyes. We can see visible light. Visible light, if you know nothing else from science class, you should remember at least the range of visible light. Visible light goes from 400 nanometers to 700 nanometers. It's a very, very small part of the entire electromagnetic spectrum. So we can't really see anything that is lower energy than red. We cannot see anything that is higher energy than violet. Ultraviolet light is what gives us our sunburns, our tans, because it has higher energy. It's actually able to burn our skin. So if you use tanning salons, you're burning your skin, you're damaging your DNA. If you're sunbathing for too long outside, if you're going to the beach and you're not putting on sunscreen, you are being exposed to ultraviolet radiation. Very high energy, very painful. And the opposite is infrared radiation, which is lower than red, lower energy than red. The wavelength is longer than red. And that you can see that from the slide, it almost borders on the microwave. So, I mean, some microwaves, I would argue, are partially infrared radiation, but infrared radiation is a little bit smaller than microwaves. Either way, they both feel like heat to us. So whenever you feel like, oh, something is hot, if you've ever standing in front of a fire and you can feel the warmth, or if you've ever been to like Universal Studios and you've seen that show with the explosions, you can feel like the heat of the explosion as it happens. Well, you're not feeling heat, right? You're feeling the infrared radiation being emitted from that fire. So our bodies perceive infrared radiation as heat. We also use it for remote control. So like when you guys open your car, when you guys change the channel. Fun trick, get the remote control, and in the front there should be like a little light bulb. If you take your camera and look at the light bulb, you can actually see the beam of infrared light coming out of it. Your phone can see it. It interprets it as a really blinding white light, but our eyeballs cannot see it. So it's really cool, very interesting stuff. And then, of course, on the very, very edge, we have the cosmic rays. Those are what gets emitted by the black holes. We have gamma rays. That's what turns you into Superman, but don't try it. You're just gonna dissolve your DNA. X-rays, of course, we all have experience with X-rays. We take them whenever we go to the doctor. The doctor tells you, okay, here you go, stand still. It'll be safe. And then they run all the way to Greece and they press the button. So, and then on the other side, we have radio waves, which is what we use for Wi-Fi, for radio. I don't know if you guys still listen to the radio anymore, but it used to be that, we have AM amplitude modulated and FM frequency modulated radio waves. AM goes a lot longer because the wavelengths are literally like miles long. Like one wave could just span miles. Whereas a cosmic ray, like it's just going up and down so fast, the wave that it has a lot of energy. And so there's two ways we can describe the entirety of the electromagnetic radiation spectrum. We can describe it in terms of frequency, meaning like what is the frequency that it goes up and down, or we can describe it as wavelength, meaning how long is the actual wave. And you can see that there is an inverse relationship between frequency and wavelength, because if you're a wave and you're going up and down really fast, well, your frequency is high, right? But that also means that your wavelength must be low because the only way you can go up and down that quickly is if the wavelength itself is short. So usually, not usually, the relationship directly is that if you have high frequency, you have a short wavelength. And if you have a low frequency, you have a long wavelength, and they are inversely related. So you can see down here, we have this equation. It says the speed of light. This is simply the wavelength times the frequency. And that just gives you the speed of light. The speed of light is a constant. It does not change. It's 3.0 times 10 to the 8 meters per second. We are in a science class, so we use science. So we use science units, metric units. For the energy, it's just Planck's constant times the frequency. H is a constant. You can always look up that value. Or you can just reformulate it as H times C divided by lambda. In this chapter and in general, whenever you see lambda, that funny little triangle in the slide, that means wavelength. And then the mu, the curvy V, it's called mu. That one is the frequency. So h mu is Planck's constant times the frequency, or hc over lambda. Lambda is the wavelength. And you can see that since lambda is at the bottom, there is an inverse relationship between frequency and wavelength. So any questions about this? This should be just basic, high school physics review. If you learn nothing else, you should always know, just like you know that the mitochondria is the powerhouse of the cell, you should always know that visible light is 400 to 700 nanometers. Everything above 700 nanometers is infrared. Everything below 400 nanometers is ultraviolet. So any questions about the slide before we move on? Okay. So what exactly does this mean? Like, okay, we have the electromagnetic radiation, but what does it mean? Well, this radiation interacts with matter, right? So for example, if you look around your room, you can see things that have colors, you can see things that have different textures. All of that is only possible because the light is interacting with the object and is being reflected or diffracted or diffused back to your eyeball. And depending on how that works, a surface can look smooth, it can look rough, it can let light in and be transparent or translucent, or it can scatter all the light and be opaque. Well, that's only in terms of visible light. And again, visible light is very, very small part of the whole thing. And for other aspects, for other energies, we can use them for different things. So for example, radio waves are used in that big instrument that I showed you guys in the hallway. That is called a nuclear magnetic resonance. It can tell you how many hydrogens are around a carbon because the waves are enough to stimulate the spin of a proton. That's very fancy terminology, but you'll learn more about it next semester. But we use radio waves for that. I'm sure you guys saw on the news recently that scientists have figured out how to use Wi-Fi to find out who is in the room, right? It used to be a conspiracy, now it's real. Well, that's another use of radio waves as well. Radio waves are about the same length as our bodies, so they resonate with our bodies and they're able to reflect or absorb or scatter. And so scientists are able to use that to figure out who's in the room. So yeah, that's one of the use for radio waves. Of course, we can use it to transmit music as well. So Wi-Fi, radio, the new spying tool from the government, that's all radio waves. For infrared, we use IR. Like I mentioned, we can use it for remote controls. Visible and ultraviolet, they have their own spectroscopy. We call that UV vis, like ultraviolet visible. We did an experiment in 111B with UV vis. If you guys remember, we were putting the stuff in the instrument and we had to take the measurements and we had to measure absorbance and blah, blah, blah. All of that was UV vis spectroscopy. And of course, there's X-ray spectroscopy, right? I took a class last semester called X-ray crystallography. The X-rays are so small, they're actually the size of the bonds themselves. So we use X-rays to figure out the actual atomic arrangement structure, and we can actually tell you the actual size of the bond length because X-rays are that small. Um, Cosmic and gamma rays, I'm sure they use that in the Large Hadron Collider to figure out, how to make black holes and create more Mandela effects and switches to separate timelines. But in short, we figured out how to use the entirety of electromagnetic spectra. You can thank Maxwell for that. If you've ever heard of Maxwell's equations, you can find out a lot more about electromagnetic radiation. But this is not physics, this is organic chemistry. So thank you to the physicists for figuring out how to use this. We are going to use it to analyze our molecules. So any questions? Yeah, and again, I cannot emphasize that there is a large amount of energy. There's a large range in the electromagnetic spectrum. We only see about 300 nanometers of it, like 300 nanometer range between it. Like everything we see is just visible light. So we're missing out. There's probably beings of infrared energy that are like right next to us and we can't even see them. That's just how it is, Ask your dogs. They can probably see different wavelengths. Alrighty. So any questions about this? Okay. So how exactly does that happen when we talk about things being absorbed or things being released? What exactly is happening? Well, you might remember also from 111A that we talk about N energy levels, right? N equals 1, N equals 2, N equals 3, N equals 4. So what happens is the electron is the carrier. It is a particle that carries or expresses the electromagnetic force. We have four fundamental forces in the universe. They're gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. I'm sure there's more, but that's all we know about. So the electron specifically carries the electromagnetic force in the universe. And so what happens is a photon can strike an electron, and if the frequency of the photon is the same as the difference in energy between n equals 1 and n equals 2, that electron will absorb the photon and use that energy to move on to the next level. You can think of it as food. You could think of it like fuel, if you will. But here's the thing. It has to be very specific, right? It has to be very specific. You've heard of quantum physics. The reason it's called quantum is because there's very specific energy amounts that the systems can occupy. So, for example, imagine there was a road where instead of being able to travel anywhere between 10 and 20 miles per hour, like let's say you can do like 10 miles, 11 miles, 12 miles, 13, 14, 15, you could only travel in multiples of 5. So your speed can only be 0. Your speed can only be 5. Your speed can only be 10. Your speed can only be 15. Your speed can only be 20. That's what we mean by quantized. There's only certain multiples of energy allowed. You could never travel at 17 miles per hour because that's not the energy that is allowed. It gets really weird. Again, this is not a physics class, so if you want to learn more about quantum physics, you can take a whole bunch of classes. But in short, to go from one energy level to the other one, you need an exact amount of energy. Any higher than that, and you're not going to transition. Any lower than that, you're not going to transition. So you need a specific amount of energy, delta E, to go from the lower energy ground state to the higher energy state. So if you stay in science, you will discuss this a lot more. But this is just some review from 111A. You can keep looking at it. And of course, the higher the difference between n equals 1 and n equals 2, the more energy you'll need to absorb. That's why some molecules only need visible light, and other molecules need radio waves. Other molecules need ultraviolet, maybe more to get excited. So for example, to produce X-rays, we actually have to excite a core electron in the copper atom. We excite it from the inner shell to the outer shell, and when it falls back down, the energy difference is so high that it releases an X-ray. And that's what we use to generate X-rays in our machines. We use copper, we call it copper alpha K1 radiation. So we figured this out. It's how it works. We don't know why it works, but you need a specific amount of energy. So this goes back to what I was telling you last week, that it just so happens that the energy difference between two bonds vibrating or one bond vibrating happens to have the same frequency as infrared radiation. And so when an infrared photon hits the molecule, that bond vibrates at the same frequency because it's absorbing that photon. And so depending on the energy, you can excite the electrons. If you have lower energy, you don't have enough energy to transition from n equals 1 to n equals 2. So all you can do is push the molecule or rotate the molecule or vibrate the molecule. So any questions about energy states? This is just review. You're not really expected to, we're not going to ask you a question about delta E or anything like that, as far as I know, but you should have it in your head that, oh yeah, look, the energy is being absorbed. It's going to a new state. It could be an electronic state if the electron changes from n equals 1 to n equals 2. It could be a rotational state. It could be a vibrational state. We call all of these points states of energy, right? So think about yourself as a human being. You wake up, you're in the awake state. You go to sleep, you're in the asleep state. You're like spacing out, you're in the daydream state, right? Human beings can have different mental states. Well, atoms can have different energy states. Does that make sense? So, again, just basic physics review. Any questions about energies? So again, the hippies are kind of right? There are different energies in the universe. And yeah, when you have an energy state that resonates with another energy state, they tend to blend together or attract. When you have different energy states, they tend to cancel out. So, law of attraction, right? Okay. So this is basically just what I told you. Imagine the HCl molecule down at the bottom. Instead of the bond, just a line, we're gonna imagine a spring. And that spring can compress and contract depending on the amount of energy that it absorbs. And so depending on how much energy it takes to absorb and vibrate, that tells you, hey, this bond is here. So for HCl, for example, Cl is a lot heavier than H. So imagine a spring with a really heavy ball at the bottom and a tiny ball at the top. Well, clearly the tiny one is going to vibrate a lot stronger relative to the heavier ball, right? And so that's going to have a specific frequency that's going to look different. Instead of HCl, let's say it was like carbon oxygen. They have similar masses, so now it's like almost having two similar masses next to each other vibrating. So that's going to give you a different frequency. That's going to give you a different energy. And so when you have your IR spectra, you're going to see those as different values and you're going to see those as different peaks and valleys. So we'll get to that. But this just says everything I just told you guys, that the radiation can get absorbed by the bonds. The bonds use that energy to start vibrating. That vibration is also a wave, and that wave can be measured by the instrument. Are we okay with this concept? It's all vibrations. It's all about the vibrations, man. Any questions so far about why this happens, what I'm talking about? Okay. And so I showed you guys last week the instrument, the infrared spectrometer. Very small, about the size of your microwave, maybe smaller. All you need to do is put the sample in there. You don't even need a spotting solution. You can just take the dry sample, put it in there, close it, select measure. I do want to point out that we don't, even though, I tell you guys that visible light is in 400 to 700 nanometers, for spectroscopy, for some reason, the spectroscopists have decided to use inverse centimeters. So traditionally, we will measure wavelength in nanometers or picometers, depending on the size of the energy. But in spectroscopy specifically, we use inverse wavelength. I want to emphasize that, so let me annotate here real quick. Right here, we have inverse wavelength, inverse wavelength. The wavelength is 1 over wavelength. And the units of wavelength are in centimeters, not in nanometers, not in meters. It is in centimeters. And so you'll see we use the mu bar right here, mu bar, to specifically call it wave number. So this is wave number. This is not frequency, this is wave number. Wave number. It's one word. And so you'll see down here, E equals h mu. Well, that mu is not wave number. That mu is frequency. So make sure you know the difference between the two formulas, h mu and h mu bar times c. And then mu bar is in centimeters, so you'll have to convert that back to meters in order to make everything work again. Regardless, the relationship is still really easy. 400 is low energy. You can see on the graph on the bottom right, 400 is low energy, 4,000 is high energy. Pretty straightforward, right? Small number, small energy, big number, big energy. It doesn't really get complicated. Just remember, though, that it is in centimeters. And you see here, wave number is directly proportional to energy. So this is just what I said. The higher the wave number, the higher the energy. And so what we do is we plot it in this graph that I showed you last week. And on the y-axis, we have percent transmittance. You can also take the inverse of transmittance, which is absorbance. Same thing, right? As long as the graph shows you the same information. Usually we do transmittance. How much light got through? Because if the light is getting through, the light is not getting absorbed. If the light is not getting absorbed, the molecule is not vibrating. Absorption equals vibration. Transmission means no absorption. Talk your way through these things. So how much if 100% is going through, none of it is getting absorbed. So anything that is close to 100, anything close to the top, like this region, this means low absorption. Low absorption. And anything closer to the bottom, this is high absorption. And high absorption equals vibrations. Does that make sense? And so it just so happens again that most bonds in the organic molecules are vibrating anywhere between 400 wave numbers. I'm using wave numbers now. 400 wave numbers to 4,000 wave numbers. Of course, there's probably some vibrations lower or higher than that, but for our general purposes, this is the general range that we stick to. So any questions about wave numbers, energies, IR stuff? So the graph is what you're going to be given in the post-lab quiz and in your final exam. And you're going to have to look at all of those peaks and tell me, oh, that is a hydroxyl peak, that is a CH3 peak, that is a CH3sp2 peak or whatever, right? You'll have to tell me exactly what it is. So before I move on, any more questions about this? Okay, so moving on. And then I have to clear the annotations. Okay, cool. So why IR, right? I told you guys we can use X-rays. I told you guys we can use radio waves. Why specifically IR? Well, again, we can think of it like a spring. And there's another slide, actually. I think that slide should have come first. Let me see. Nope. Yeah, right here. We'll go back to the other ones. But you could think of this like a spring, right? And again, going back to physics, there is a formula where you can actually go and substitute the molar masses of the atoms and find out what frequency they will vibrate at. But if you have carbon and carbon, well, that's one vibration. But as soon as you replace it with something a little heavier, that's another vibration. If you carbon nitrogen, carbon oxygen, carbon fluorine, carbon hydrogen, they are all different frequencies. They have their own unique vibration, their own unique fingerprint vibration. And so using that principle, we actually have a unique signature for pretty much all functional groups. One of your pre-lab quiz questions was, what does IR tell you? IR tells you what functional groups are present because the functional groups have different, we call it hetero nuclear bonding. So carbon oxygen, carbon fluorine, nitrogen oxygen, nitrogen hydrogen, they have different atoms in the same bond, and that gives you very specific frequencies. So they will give you a fingerprint signature. You can tell me exactly what functional group it is based on where it is in the IR spectra. Any questions about that? Okay. So one of your other questions was true or false? All molecules are IR active. That is false. All molecules vibrate, but that doesn't mean that you can see all molecules in IR because you need very specific conditions to be able to see a molecule in IR. The first one is that it has to have a change in the dipole moment. In other words, it has to be polar. But not only does it have to be polar, it also has to be asymmetrical. Because if you have a polar bond, but the whole molecule is symmetrical, they cancel each other out, right? The bonds are symmetrical, they'll cancel each other out. Um, you're not going to see it in IR, even though the bond is polar. So it has to be polar and it has to be asymmetrical. There has to be no symmetry. Only then can you actually see it in the IR spectra. Does that make sense? So again, all molecules vibrate, but not all molecules will be detected by infrared spectroscopy based on their symmetry and based on the bond polarity. So you see here in blue, the greater the change in the dipole, the more intense the absorption. And that makes sense, right? Because remember, wave number is a measure of energy strength, 400 to 4,000. Well, if you have a polar bond, that's a very strong bond. Polar bonds are strong bonds. They're hard to break. So when that happens, well, you need more energy to vibrate it. So polar bonds tend to be higher up in the IR spectra compared to non-polar bonds. And as you see here at the bottom, you have a hierarchy. CH is weaker than NH. NH is weaker than OH. So OH will always be higher than NH. NH will always be higher than CH. It also depends, right? We have different types of movement. We have like wagging and bending and stretching. So depending on that, that also will show you the different signals in the IR spectra. But what I want you to take away from the slide is that in order for it to be IR active, it needs to have a change in the dipole and it needs to be asymmetrical. Any questions so far? All right. And so I'm going to show you some really cool animations about this pretty soon. So again, we need to drive the point home. We can think of this as a spring. The spring is vibrating. And these motions here are the motions that I showed you last week. Remember, I showed you the molecular vibration yoga. You can have like stretching where, it's going in and out. You can have like asymmetric stretching when one arm is coming in, one arm is coming out. You could have bending where like both of them are going in the same direction. You could have like a twisting where they're coming out of the plane. And this is just for like a 3-atom molecule. Imagine something with more atoms. Imagine something with like a giant chain of carbons. Imagine something with like 20 carboxylic acids in it. You can see a lot of motion in the molecule. And so again, in general, stretching takes more energy than just bending. Bending is simple, right? Think of the difference between actually forcing somebody to move their arm versus just pushing them. It's a lot easier to push somebody than to grab their arm and force them to move their arm up and down, left and right, right? Like, have you ever played with your siblings and you grab their hand and you're like, slap me, right? And they're trying not to slap you. Like, it takes more energy to stop them than it would just giving them a small push when they're not looking, right? Be kind to your siblings, but if you have siblings, you understand. So yeah, there's all sorts of different motions that molecules have. And so in general, if you see something in the higher wave numbers, we call that a stretching vibration. If you see something in the lower wave numbers, it's most likely a bend or a wag. And if you look at the bottom, we have an example, carbon dioxide. Some stretches are visible and some stretches are not visible. So again, all molecules vibrate, but not all molecules show up in IR. And not all vibrations will show up in IR because some vibrations are symmetrical, and so that cancels out the the dipole chain. So you see at the bottom, when you have the carbon and the oxygens in carbon dioxide, when you have them stretching out symmetrically against each other, the change in dipole is symmetrical, so it cancels out. So this stretch, the symmetric stretch in carbon dioxide, is not visible in IR. But the asymmetric stretch, well, that one still has a huge change in dipole moments and it's not symmetrical, so you can see that one. So you can see the antisymmetric stretch. You see that it shows up at 2350 wave numbers, but you cannot see the symmetric stretch. So it depends on the identity of the molecule, and it depends on whether there is a polar change, a dipole change. It depends on the molecule. Any questions about that? All right. And then we talked about this slide already, so I'm going to skip it. But again, this is just to further drive home the point that this is just a spring. And depending on the masses of the spring and the length of the spring, it gives you different energies. I do want to emphasize the blue. Notice that it says the strength of the vibrating bond and the masses are factors. So triple bonds are stronger. So that's like having a stronger spring. So you need more energy to vibrate a triple bond compared to a double bond compared to a single bond, right? Single bonds are weak, triple bonds are strong. If it's weak, if it's a weak bond, you can vibrate it with lower energy. If it's a strong bond, you can vibrate it with more energy. Does that make sense? So that's all the slide is telling me. Okay, before we begin this right here, I do want to show you the actual vibrations of the molecules. So here we go. This is a website that I use a lot called CHEM223A. Everybody can see my screen, right? Like everybody can see the water molecule on the screen. I switched to sharing this part now. Alrighty. So this is water, and this website is called ChemTube3D. Very useful. Highly recommend that you go and look around. They have a lot of 3D structures that you can actually look at, rotate, play around with, things like that. So here I have a water molecule. And you see here on the right, there's the three different stretches that are visible in IR spectroscopy. And so right here, there's a menu. It says no vibration, model 1. Well, let's look at the first vibration. And it gives you the wave number too. So you can see here it says 1711 wave numbers. And if you click it, you'll see the motion that I'm talking about. This is the bending. They call it the bend, mu2, right here. And you can see how the water molecule is vibrating, bending towards itself. And so that vibrates at 1711 wave numbers. So if you look at an IR spectrum of water, you will observe a peak at 1711 wave numbers that corresponds to this specific vibration because it takes a photon of infrared energy of this exact energy to create this exact vibration. It's very, very specific. And so we have another vibration at 3730. Notice the wave number here is a lot higher. That means that this vibration takes more energy to create. And you see here that is the symmetric stretching. That's both of the molecules, both of the atoms coming closer towards the oxygen at the same time. And we have one more vibration, which is the highest one at 3851. And this is the asymmetric stretching. So one is stretching out while the other one is stretching in. Just like that. So again, business idea, you can start a new yoga studio and talk about how you can move like water, work out like water does. Right. This is basically one way to do it. And another cool thing about this website is you can see all sorts of molecules, not just water, right? So I have vibrations of ammonia, for example. I'm going to click on ammonia, and you see I have the ammonia molecule NH3, trigonal pyramidal. Well, same thing. Let's see how it vibrates. You see, just by adding one more bond, I have added significantly more vibrations. So the simpler the molecule, the less peaks that you will observe in the IR spectra. The more complicated the molecule, the more peaks you will observe. So that's also an indicator. If you have something that is complex and you only see a few peaks, something went wrong. If you have something that is very simple and you see a lot of peaks, there's probably some contamination or something else in there. But let's take a look. So you see the first vibration is at 11, it's at 1132 wave numbers. So 1132 wave numbers. It's very similar to the water one, right? This is the same, the bending. It's bending towards the bottom and it's pushing the hydrogen up. So that's one vibration. We have another vibration here, which is like an asymmetrical out of plane bending. This looks like you're doing back day, like doing the rows or whatever it is. We have another vibration at 1727, which is very similar to that first one I showed you. And notice that these motions are bending motions, right? The bonds are just being bent. The bonds themselves are not vibrating like springs. This is just like you bending the spring like a slinky, right? These are all bending motions. And notice that all of the bending motions are at 1,100 wave numbers, 1,700 wave numbers. Bending motions take less energy than stretching motions. So I'll show you a stretching motion now. Look at this one. I wish somebody did this to my back. That would be nice. Look at that. So it's being symmetrically bent outwards and inwards. That's one of the bending motions. This one happens at 3433. Here's another bending motion. This is more asymmetric bending, right? Here's another bending motion at 3565. So one of them stays the same and only two of them are like jamming. Also an asymmetric one. And all of these are visible in the IR spectra. So you see that ammonia has 6 peaks, 6 vibrations, whereas water only had 3. So let's pick something a little more complicated. Go back to molecular vibrations. Let's do benzene. Benzene has 6 carbon hydrogen bonds, and it's a highly symmetrical molecule. So here's benzene right there. Let's see how benzene vibrates. Look at that. Look at all the vibrations possible with benzene. So when you plot this in an IR graph, you're going to see a lot of peaks. I'll explain a little bit more, but usually we kind of ignore anything under 1,000. It's really hard to prove which one is which. I just learned this semester actually that you can predict all of these vibrations with mathematics, but it's group theory. It's the same mathematics that they use to solve the Rubik's Cube. Uh, just just look at the CHEM2. It'll give you the list and you can actually see it. If you take spectroscopy, physical chemistry in upper division class, you will be learning the formulas on how to calculate all these vibrations. But it's a lot of math, but for the sake of demonstration, I'm only going to show you the stretching vibrations. So look at this one. Again, that looks real nice, right? Whole molecule is getting stretched symmetrically. This takes the most energy. Look at the wave number. It's at 3385. This would be a carbon-hydrogen symmetrical stretch. And then right below that, you have an asymmetrical stretch. Right below that, you have another asymmetrical stretch. So all of these in the 3000s are stretching vibrations. And again, all of these in the 1600s, they're probably bending vibrations. So you see here, the molecule's kind of bending a little whack. Here's another one. That one kind of looks like a spider climbing up. Let's see this one. Yeah, that one's interesting. So again, you can go on ChemTube 3D yourself and take a look at it. You see the one with the lowest wave numbers? These are more bending, so we call this out of plane bending. You see like the molecules are being bent out of the plane. This one occurs at 996 wave numbers. The weakest one would be this one. So you're just slightly pushing up the molecule up out of the plane. But notice that the bonds themselves are not stretching or contracting. So this is what we mean by bending vibrations. So are we okay with this concept? Like, are you guys kind of seeing it a little better? It's better when you see it, right? We don't expect you to calculate how many vibrations. We don't expect you to like tell me which vibration it is. I will expect you to tell me that something that has a high wave number is more likely a stretch. Like if I tell you, hey, a vibration has a wave number of 2000, is that a bending or is that a stretching motion? Well, stretching motions require more energy, so you should be able to tell me that's a stretching motion. When you describe it, if you tell me that a stretch is a bend, it's going to be wrong because it's very easy to tell the difference. Again, you can clearly see here. See, you have a category of peaks below 1800, and suddenly it makes a jump to 3000. All of the ones that are at 3000 are stretching. Anything below that is bending. That is an IR principle. You should know that bending has less energy than stretching. Okay? So that is something that you do have to remember. Let's see if we can do one more, something interesting. Iron pentacarbonyl. That one sounds fun. Phosphorus pentafluoride, vanillin. Let's do vanillin actually, because we're actually going to do vanillin pretty soon in lab 6, I believe. So let's see if vanillin will load. There you go. So this is vanillin, right? So before we even look at the stretches, I can tell you there's going to be a stretch from the carbonyl, carbon-oxygen double bond right here. There's going to be a stretch from the hydrogen-oxygen hydroxyl group, and there's going to be a stretch from this ether, this carbon-oxygen bridge right there. Those are going to have very characteristic stretching, and you can see that in the IR spectra. So let's see how many vibrations we have here. Oh my God, look at that. The weakest one is at 71. Let's look at that one. Well, that's just a bend, see? No molecules, no bonds are being stretched. They're just being bent. It's out of plane bending. You see that? And that is strictly caused by that methyl group just bending out of plane. The whole molecule is actually pretty chill. And so let's look at the strongest one, 3783. You see that? The highest wave number vibration is only for one functional group. Look at that. So that will only be one peak. So you can look at the IR spectra at 3783 and be like, wow, that is only the OH vibration right there. It's a polar bond, so it has a lot of energy to vibrate. And there is a change in polarity when the hydrogen gets closer to the oxygen. And so that creates an IR active vibration. Let's look at the next one. This one here, this is an sp2 carbon-hydrogen vibration. sp2 is a double bond. It's a lot stronger than a single bond, so it's going to take more energy to stretch compared to a single bond. So this is also characteristic. Here's another one. This one's asymmetric. You'll notice that they're kind of similar in energy. One is 3249. The other one is 3262. Let's look at just this one, the 300. Look at this one here. This is a metal stretch. Very characteristic as well. This is the aldehyde stretch. This is a very characteristic peak for aldehydes. I will demonstrate soon. Let me see. I'm trying to find the one for the ketone. That one's at 1700. 16. Let's do this one here. Nope. 1678. Nope. 1699. Nope. Oh my goodness. That ketone is not cooperating today. I think it's 18. There we go. This is the last one I want you guys to see. This is the carbonyl vibration. Carbon double bond oxygen is called carbonyl. So whenever I say the word carbonyl, I only mean carbon double bond oxygen. And that's what that stretch looks like. So again, we'll be using vanillin pretty soon. You will get an IR spectra of vanillin when we get to that lab. CHEM223A, very cool website. Highly recommended. I still use it even today. There's another website you can check out. It's from Purdue, but this one doesn't really have like really cool animations. This is more accurate though. Like a lot of these motions are slowed down so you can actually see what they look like. But in the real world, I mean, atoms are so tiny, their vibrations are happening so fast. So this is actually a more accurate picture of what they look like. So you can see, for example, H2O, here's all of the vibrations just listed out. And it tells you the wave numbers right there. That should tell you roughly where you find the wave numbers. If you want to do something more complicated, you can click on the molecules and you can see all sorts of different vibrations and you can see exactly where they happen. Here's another one. Yeah, the bending, and notice again that the bending motions are always lower in energy than the stretching. See, CO stretching, 2174. Bending, 539. Bending, 539. This stretch, well, this is a low energy stretch, but I mean, it has to do with the sulfur oxygen molecule there happening. So in general, stretching happens at higher wave numbers. That's still a principle that I want you guys to remember. And again, here's benzene with all of its vibrations. And you can rotate them and spin them around and see what they look like. So any questions about this? Any questions about the vibrations, the molecules, anything of the sort? We're going to actually start looking at spectra. So if you have any questions about this, Now's the time to ask before we move on to the next topic. Okay. At any point, feel free to ask questions, okay? I'm going to share back to the PowerPoint slide. Okay. So now that we saw all of those vibrations, you can actually see the peaks. So these peaks, every time you see a peak, that is where a vibration is happening. And it could be the bending vibration, it could be the stretching vibration. Well, that's what we're going to learn right now. So when we look at a spectrum, spectrum is singular, spectra is plural. Okay, so when you look at a spectrum, you're going to see, again, on the x-axis, you're going to see wave number. So let me annotate with a different color now. You're going to see wave number on the x-axis. You're going to see percent transmittance on the y-axis. This means low energy. This means high energy over here. And so what you look for are three things. You look for the wave number, you look at the shape, and you look at the intensity. Intensity means y-axis. Wave number means x-axis. Shape, well, that's just shape. If you don't know your shapes, I don't know what to tell you, right? So for example, in this one, how would you describe the peak at 1500? We're close to, how would you describe this peak? Somebody tell me. What words would you use to describe that? You can unmute your mic and then say it. What words in English, Would you call that intense, not intense? Would you call that broad? Would you call that sharp? Would you call that medium? Would you call that like a strong peak, a weak peak, a medium peak, wide, narrow? What words would you use to describe this? Can't proceed till somebody says it.
It's pretty sharp.
Pretty sharp, right? Yeah, that's a sharp peak. Thank you, Diego. It's a pretty sharp peak. How would you describe this one over here? What words would you use to describe that peak? Can't move on till someone says something. We're still in class. How would you describe that peak in English words? Would you say it's sharp? Would you say it's narrow? Would you say it's broad? Would you say it's strong? Would you say it's weak?
Dull,
I'm sorry?
like weak, dull.
Weak, dull?
Mhm.
Well, I think what you mean by weak is that you're saying that it's not as sharp, right? Am I correct?
Yeah, not as sharp.
Not as sharp, yes. So this is where the intensity comes into play. If something has a lot of absorption, it has low transmittance. And you see how that peak is closer to the bottom? So in terms of intensity, we would actually call that a strong peak. The weak peak would be like this one up here. That one right there. That would be like a weak peak because it's closest to the top. If you're closest to the top, that would be not very strong. But what you were trying to say is that like it's not sharp, right? If it's not sharp, it must be dull, right? So that's what you meant. Blunt. Okay, that's good. I think the best way to call this would be like broad. This would be a broad peak. So broad peak, sharp peak. You can call this sharp. And then here, since the intensity is strong, you'll notice it's only at like around maybe 12% transmittance. That means a lot of it is being absorbed. This is actually a very strong broad peak. I would call this strong broad peak. And then this one would be a medium sharp peak. Medium, because it's kind of strong, but not really. Most of these would be mediums. And then this one up here, like I would call this one a weak sharp peak. Things like that. So, you can kind of use your own judgment to describe these compounds. There are very specific terminology that we end up using when we start doing this. So, any questions about this? So, when we look at an IR spectrum, we look at the wave number, we look at the shape, and we look at the intensity. The wave number is the x-axis, the intensity is the y-axis. So, the last thing to look at on our own is shape. And of course, as long as you're making a decent effort that is reasonable, like right now you said it was dull. Obviously, well, I can see what you mean, right? Sharp and dull, that makes sense. You don't know the proper terminology yet, so, but I do expect you to at some point understand the terminology. If I say the word broad and you draw a sharp peak, obviously that doesn't make sense. It has to be broad. It has to look broad. And you'll see what I mean. You'll see what I mean by that. So, any more questions about this? Okay, I'm going to clear the drawings and I'm going to move on to the next slide over here. So let's see. Alrighty. So here we go. Now you guys get to know the dark secrets of the dark magic. We know where these bonds are. It's not really a guessing game. I'm not gonna be like, oh, which one of these it is. You pretty much know where they are. If you look at this slide, you'll see the fingerprint region goes from 600 to around 1400. Some chemists will tell you that it's, anything under 1200. Some chemists will tell you anything under 1000. Some chemists will tell you that they don't believe in a fingerprint region because the information is just as important. Yeah, sure, but most fingerprint region vibrations are bends, out of plane bending, wagging, bending, things like that. And so the fingerprint region is kind of there as a last resort. Like we really have a hard time telling it apart. Now we got to go look at specific fingerprint stretches or bends. So we don't really look at the fingerprint that much. We do for some things, like esters are between like 1000 and 1300, but we don't really look at it for the majority of molecules because, and by molecules, I mean functional groups because most of the functional groups have heteronuclear polar bonds. They have different atoms and they are polar and they are asymmetric, so they will often just be in the higher numbers. So you see that if you go to the higher wave number area, between 2700 and 3500, this is the NH, OH, CH stretching vibrations. High energy. We teach you guys that carbon hydrogen is not a polar bond. It's not, but there is a difference in polarity. So there is a dipole, not as much as nitrogen, not as much as oxygen, but it's there. So we do see it in the higher regions. Triple bonds, we see that between 2000 and 2500. Double bonds, we usually see between 1500 and 1800. It depends. A very iconic characteristic bond that you absolutely must know in this class is this one, the carbonyl bond. The carbonyl is so iconic, it is like not knowing who Bugs Bunny is. It is like not knowing who SpongeBob is. It is like not knowing who I don't know, Gandhi is, right? Like the carbonyl bond is like the iconic bond of the IR spectra. If you don't know anything else, at least know where to find carbonyls. Because if you can't find carbonyls at all, then I don't know what else to tell you, right? So make sure that you at least definitely know the carbonyl bond. That one is so iconic and characteristic that like you can't take organic chemistry without ever hearing about the carbonyl peak. And that one is usually found between 1600 and 1800, depending on whether it's a ketone or a carboxylic acid or an amide or an aldehyde. It depends, but it's still going to be within that region. So, and this is also not 100% absolute. This is chemistry. There's always that one tiny little exception, but for about 95% of the cases, this chart is generally true. And I believe in the final exam, you will be given a list. I'm not sure yet. I have to double check. But you will be given a list of the vibrations and where they are located. But I think you should just learn where they are in general, right? Like you should be able to look at a chart and tell me, oh yeah, there's an alcohol. This is a carboxylic acid. There's a carbonyl. The carbonyl is part of the carbonyl looks like it could be an aldehyde. You could see an sp2 carbon hydrogen peak. You need to know how to do those kinds of things. So wait, go back there. Okay, so any questions about this slide right here? I will also pass out next week when we go and meet in person again. I will pass out a chart that shows you where things are as well. So any questions about this right here? Okay, so we're gonna move on to the next slide. So again, let me delete the drawings, clear all my drawings, and then next one. Okay, so let's start with the very first one. No functional groups at all. Just carbon hydrogens, just hydrocarbons by themselves. So again, the more types of bonding you have, the more peaks that you're gonna observe. And in this case, we only have carbon hydrogen bonds and nothing else. So any spectra that looks relatively simple like this, you are going to see it to assume, well, there's probably not many functional groups, and probably it's an alkane, an alkene, or an alkyne, either a single bond, double bond, or a triple bond. Which of the three is it? Well, that depends, right? Remember we learned hybridization. Alkanes are sp3 because they're all single bonds, tetrahedral. Alkenes have a double bond, so they can be either sp2 or sp. Alkynes are always sp, and so the more S character that you have, the lower your wave number. The more S character, the lower your wave number. Make sense? Or I think it's backwards. Well, let's explore it. Alkane, sp3, so that's a lot of p character, right? You have three p orbitals blending with one s. You see the wave number is between 28 and 32. Look at the alkene. The wave number is between 32 and 28 as well, but it looks like it's a little bit higher than just the alkane. And then if you look at this one, CH triple bond, it's over here by 3300 at the bottom right. You see that? So actually, I think my statement was backwards. The more S character you have, the higher wave number that you have. So SP only has one p orbital. It's still mostly S. SP2 has two p orbitals. SP3 has three p orbitals. So the more S character, the higher the wave number. Let's rephrase that. Another way you can think about it is just look at the bonds, right? A triple bond is stronger, so it's going to have a higher wave number. A double bond is stronger than a single bond, so its wave number is going to be higher than a single bond, right? It's about bond strength. This is just another perspective. If you're still not familiar with your hybridization, that's fine. Think about it in terms of strength. And so you see here, I want to emphasize where the peaks are. Let's see what happened now. Annotate. I have to draw them. And I have to pick a color. Here we go. Okay, so here the peaks are just this whole thing, like this whole thing right here. I call those the stalagmites. That's always present in all molecules because in organic chemistry, it is the chemistry of carbon. Carbon will bond to hydrogen. Every organic molecule has CH in it. So every organic molecule is always going to have this right here. This whole thing that you see right here. I call those the CH3 stalagmites. That is always present. That is not iconic. That is not something that you can use to give me any confirmation about anything because that's always there. That is always there. So it's something to look at. If you have nothing else but that, you can tell me it's some sort of alkane, alkene, or alkyne. But if you have other stuff, it's pretty useless because, of course, there is a carbon-hydrogen stretch. It's an organic compound. Everything has carbon-hydrogen in it. That is organic. So that's always going to be present in all of your spectra. The only time it makes a difference is if you see, you notice there is this peak, very sharp, weak peak next to the stalagmites. That peak only comes from the carbon double bond. And then you see this sharp peak over here further away. Notice there is this distance right here. This one is specifically only from the sp carbon hydrogen bond. So this will tell you if it's a double bond or a triple bond, but even those you'll notice still have all the stalagmites in there. So these are these are everywhere. Every spectrum has this. So be careful, right? I see a lot of people, they kind of just tell me like, well, this is a CH3 stalagmite stretch. Well, that's cool, bro, but everything has that. You could have said that about any spectra. That doesn't really tell me you know what's going on. Okay? So again, you can think about it in two ways. More S character, higher wave number. Less S character, lower wave number. Or, to avoid confusion, like me, just think about the strength of the bonds. Triple bonds are stronger, they have a higher wave number. Single bonds are weaker, they have a lower wave number. So any questions about this? And also notice, some of you might be looking over here and being like, well, what about this? We only pay attention to very specific regions. That could be another CH band. I don't know. It's something. I'm not looking at that. I'm only looking at the stalagmites and I'm looking to see if there's other peaks in between. Since I see the stalagmites and nothing else, it has to be only a hydrogen carbon compound. There are no other functional groups in it. So in IR, we are selective with what peaks and what regions we're looking at. We don't analyze the whole spectra. We only look at certain parts of the spectra to give us the information that we need. So any questions about alkanes, alkenes, alkynes? And it'll make more sense as we continue on to the next example as well. So I'm going to clear the drawings. I'm going to move on to the next slide. Okay, so here's octane, right? Nothing else in it. Hydrogen, carbon, nothing else in it. Notice how the spectra looks really simple. There's nothing except the stalagmites between 2800 and 3000. And again, these are always there. These will always show up in all compounds. This is not necessarily useful in terms of identifying what you have. This is always there. These, well, they'll show up, but which is which? Again, take quantum mechanics to figure out which is which. You can tell me that they're bending. As long as you can tell me these are bending vibrations, you will be considered correct. Which of the two is it? Bro, that doesn't matter. Just tell me that these are bending and tell me that these are stretching vibrations. But notice there is no carbonyl, there is no carboxylic acid, there is no amine, there's no amide. It's just an alkane, nothing else. Now compare that to the next example. I think I can just scroll. Yep. This one here is aromatic, right? Aromatic compounds. It still is a hydrocarbon, but now there's double bonds and sometimes there's rings. And actually it's a bond and a half because it's resonance. So notice that you also have the stalactites right over here. You have like this region that looks like the stalactites on a cave, you know, the little pointy rocks on a cave. That's what I call them. But notice that, first of all, the intensity is not as much as the other ones. So the intensity here is lower. Why? Because the double bond is stronger. So it doesn't absorb as much energy. It's harder to vibrate it. So it's not going to be as intense as a single bond where it's weak. So it can absorb a lot of energy and it can vibrate a lot. And also notice there's very specific peaks that are only part of aromatic hydrogen carbon bonds. Very sharp medium peaks. Here's another one. This is a carbon-carbon aromatic double bond stretch. Very sharp, always found between 1500. This one right here. This is 1500. Not exactly at 1500. Maybe it's 1450. Maybe it's 1550. Maybe if your instrument is not very well calibrated, it might show up at 1600. These are not absolute values, but the regions are general. Generally, you find them. What are these combination bands? I don't know. That's probably, I mean, I showed you the benzene vibrations. It's probably the one where you have like half of the molecule vibrating in and out of the plane. Look at the fingerprint region. That's a CH bend. Which one? There's 6 CHs. I don't know. It doesn't really matter which one it is, right? What is this? We don't even bother telling you what it is because it's not very important based on what we're looking at. So what we're looking at is specifically for this one, the ARH stretch and the aromatic C double bond C stretch right there. So if you see those two specific ones, if you don't see a lot of functional groups, that's most likely some sort of ring. So in this case, it would be methylbenzene. You can see the structure is right here. It's just a methyl group with a benzene ring. So any questions about this? Okay. And so let's see. Other functional groups, well, the carbonyls, right? We talked about the carbonyls. The carbonyl groups are carbon double bond oxygens. Let me see. I think they're supposed to be, there you go. Carbon double bond oxygens. So there's basic functional groups and there are compound functional groups. The basic one is just, for example, carbonyl, carbon double bond oxygen, right? We call that ketone. If there's nothing else, we call that just ketone. But usually if there's anything else, we call it an entire new functional group. So an aldehyde, a ketone, an ester, a carboxylic acid, and an amide, they all contain carbonyls. Let me write that down. They all contain carbonyls. And you need to not confuse the terminology. Carbon double bond oxygen is called carbonyl. So when I talk about a carbonyl, I'm specifically only talking about the carbon and the oxygen double bonded to each other and nothing else. This is just carbonyl. If I use the actual name, I'm talking about the whole group, the carbonyl and whatever else is attached to it. Does that make sense? Carbonyl is only for carbon double bond oxygen. If you're going to talk about a carbon double bond oxygen in IR spectroscopy and you give me the peak, you got to tell me this is a carbonyl peak. Because if you tell me this is a carboxylic acid peak, well, which one? In a carboxylic acid, you have a carbon double bond and you have an OH. If you tell me this is a carboxylic acid peak, which one? That's not correct. You have to be specific. They both have different vibrations. If you tell me this is an aldehyde peak, same thing. Which one? Is it the carbon double bond? Is it the carbonyl? Or is it the carbon hydrogen stretch? Look at the ester. Is it the carbonyl or is it the carbon single bond? Look at the amide. Is it the carbonyl or is it the N whatever? You have to be specific. Carbonyl is only the carbon double bond oxygen. The other names are the whole complete molecule. Okay, so when you're telling me peaks, you have to tell me this is a carbonyl peak of an aldehyde. This is the carbonyl peak of a carboxylic acid. This is the carbonyl peak of an ester. Okay, be very specific with your language. It matters. It really does matter. Okay, so just like I mentioned, the more polar the bonds are, the stronger they tend to be. So look at the carboxylic acid, right? Very polar. This carbon right here in the center has two dipoles. You have the carbonyl dipole and you have the carbon hydroxide dipole, right? So that one should have a higher wave number because that's a very polar bond. And sure enough, look at that. This is at 1710 to 1780, 1780. Now look at just a ketone. A ketone only has one dipole, the carbonyl dipole. So it should be a lot weaker. And sure enough, look at the numbers, 1680 to 1750. It depends, right? Maybe there's a carbon with a chloride over here in one of the R groups. But in general, the more polar the bonds, the higher the wave numbers, right? Look at the ester, carbon double bond oxygen, carbon oxygen. That's also two dipoles. So you would expect esters in general to show up between 1735 and 1750. And you see an aldehyde, well, that's just one. This one right here is not as strong as this one. So it'll still be strong. You can see it sometimes shows up at 1740, but it starts off at 1690, very weak. And then the amide, well, same thing, right? This N right here, um, it distributes the dipoles differently. There is a dipole, but this one is not as strong. And then there's no hydrogens here, so the NC bond is not very polar in general. There's another one this way. So this one has a little bit less. But again, these are general regions. These are general areas. They don't always show up exactly at these numbers. And I am not personally going to ask you to tell me, hey, here's a carbon double bond peak at 1800. You have to tell me that it's an anhydride. No, 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 no. Oh, I saw one at 1735. It's an ester. I mean, it could be anything, right? It always shifts. It always shifts. As long as you know, as long as you know that the carbonyl is between 1630 and 1780, and you know how to find it because it's a very strong, I wouldn't say sharp, but I would say sharp-ish peak. You need to know where the carbonyls are. Like if you can't, if you learn nothing else from my class, please at least know where to find the carbonyls. Because if you can't find carbonyls, I mean, oh, I know how to do IR. Okay, show me. And you miss the carbonyl? That's like again, that's like not knowing who Bugs Bunny is. That's like not knowing who SpongeBob is. That's like not knowing like that the Pope exists. Like I mean, I can think of a million examples, right? You need to know the carbonyl at the very least, please. So let me once again clear the drawings. Let's see, clear my drawings. Now it's not clearing the drawings. I don't know why. Oh, that's because I'm not in drawing mode. Hmm. Okay, well, I don't know what happened there. Okay, so here's an example. We have 2-heptanone and we have butyraldehyde. Both of these are carbonyl compounds. You see, I am circling the carbonyl in red. However, one is an aldehyde and one is just a ketone. How do I know? Because of the nomenclature. How do I know? Because of the structure. You see, this is just carbon double bond oxygen RR. That's a ketone. The bottom is carbon double bond oxygen hydrogen. That, by definition, is an aldehyde. And so let's compare the two spectra. You see, I'm going to use the color blue for the carbonyl. So right here it says carbon double bond stretch. This peak, notice how strong it is. Look at that. This is a very strong, sharp peak. I would call this strong and sharp. And I'm sure you agree. I mean, look at that. There's almost 100% absorption right there. That is a very strong polar bond right there. And that one is very characteristic of carbonyls. If I give you a spectra, the very first thing you should look for is the carbonyl peak. Where? In the 1700-ish. Look around 1700 for this very strong peak. Look at the bottom one, butyraldehyde, carbon double bond oxygen, 1720. Look at the shape, look at the size. This is also a very strong, sharp peak. Do we all agree? The only difference is that for aldehydes, there is going to be a carbon-hydrogen stretch, and that's going to show up as two additional peaks right over here at 2720 and 2820. You see? These two are considered the CH stretch right here, the carbon-hydrogen aldehyde stretch. And how do I know that it's a carbon-hydrogen? Because look at the rest of the group. These are the stalagmites, right? Stalagmites, stalagmites, yeah, because it's ceiling. These are the stalagmites that I told you about, the CH stretches. Notice how this CH stretch is also in the similar region. That's how you know it's a CH stretch. If it was CO, it would be over here with the carbon oxygens. And notice how we're ignoring the rest of the peaks. Here, we're only looking at two peaks. We're looking at the peaks right here and the carbonyl peak. Everything else, like you might be like, well, what's this? I don't know. What's this? I don't know. What's this? I don't know. We don't care about those peaks. We're only looking for the characteristic peaks of the specific functional group. Make sense? That's why even though the spectra looks confusing, you really only need to know what to look for. You only look for a very specific region. So this shows you the difference between a regular ketone and an aldehyde. Yes, you should know how to find the difference based on this carbon-hydrogen peak. Some of the questions you will receive will give you a carbonyl peak, and you'll be like, oh, well, that's obviously just a ketone. Nope, that's wrong. Why? Because you didn't see if there were any other carbon-hydrogen aldehyde stretches. And that only happens with practice. You can only do practice with this, and you get better as you do it. So are we okay with this concept? Like, do you start seeing now the difference between the CH stretches, the carbonyl stretches? The fingerprint region is kind of just there. We don't really pay much attention to it. We don't label all of the peaks. We don't always talk about all of the peaks. We only want the peaks relevant to our functional groups. Make sense? So any questions so far? Okay, we're doing good on time. Let's move on to the next example. Let's see. Once again, clear all the drawings and next. Oh. Okay, here we go. So when it comes to carbonyls, we have to talk about conjugation. I don't know if you guys have mentioned conjugation in your lectures, but conjugation is just an alternating single double bond. So let me draw an example for you guys. If you have like double bond, single bond, double bond, single bond, double bond, single bond, double bond, single bond, dot, dot, dot to infinity, right? Or maybe you have, carbonyl, double bond, single bond, double bond, single bond. Anything that has alternating single double bonds, we call that conjugated. Conjugation. Conjugation means alternating single bonds and double bonds. So benzene is conjugated because it has alternating single double bonds. Carbonyls that have alternating single double bonds are part of a conjugated system. Conjugation creates resonance. Resonance weakens the bonds. Weaker bonds have lower wave numbers. You see, it's one if then statements. This is all if this is true, then this is true. So if you have a molecule and you know before you put it into the IR that you have a conjugated system, you can prove that you created the conjugated system if it's part of your synthesis by seeing if the carbonyl peak shifts to a lower wave number. So you see down here we have a ketone, carbon double bond oxygen, single bonds all around, not conjugated. Notice its wave number is 1720. Well, as soon as I add this double bond, I begin to add conjugation. I introduce resonance. I weaken the bond. So you notice that the number goes from 1720 to 1680. Why? Because the resonance spreads out the bond like butter on a bread. You know, you spread out the butter all over the bread. Now the flavor is more spread out. Now wherever you bite, you don't taste as buttery, right? To give you some sort of analogy. So conjugation makes the bonds weaker. It lowers their wave numbers. Does that make sense? Because it's a 1.5 bond, right? You used to have a double bond. That's a strong bond. Double bonds are stronger than single bonds. But once you add resonance, once you add conjugation, you're making that double bond into a 1.5 bond. And obviously, 1.5 is less than 2, so it's weaker than 2, right? I think it makes sense straightforwardly. This would only be confusing if you don't know what conjugation means, if you don't know what is a conjugated system. A conjugated system is just alternating single double bonds. Think of benzene. Think of vitamin A. That's why it's orange, right? Vitamin A in the carrots is orange because the whole molecule is just a conjugated chain. And that creates a system that absorbs indivisible light. And that's why we see it as orange. Okay, any questions about this? All right, so next slide. Alcohols and phenols, right? Make sure you know the difference. Alcohol is just OH, so this is just alcohol. A phenol is specifically the benzene ring with the alcohol. So this is a phenol, and this could be anything else. So alcohols and phenols. Even phenols are made of alcohols. So they all should still have the same rough stretches. One of the things that makes this unique, excuse me, one of the things that makes this unique is that there's hydrogen bonding. Remember hydrogen bonding. That means that oxygen, hydrogen, nitrogen, hydrogen, and fluorine hydrogen can make hydrogen bonds to other oxygens, nitrogens, and fluorines. When that happens, you're increasing the restriction on the bond. You're increasing the requirement of energy to vibrate those bonds. So when you introduce hydrogen bonding, you're increasing wave numbers because you need more energy. Remember, big wave number, big energy. Small wave number, small energy, right? So you want big wave number energy to prove that you have a hydrogen bond in your molecule. Make sense? And also, some of the molecules are probably hydrogen bonded, and some of them are probably not. So you actually get like some sort of Gaussian distribution when you see your signal. And if you look here at the example, 1-hexanol, you see that the OH stretch is very broad. This is so characteristic of the alcohol. Like you can only, if you see this structure in any IR, 80% of the time, right away, it's an alcohol. 80%, because again, there are exceptions. And also, this is the result of hydrogen bonding, which also happens in NH and FH. So you do have to be careful. But 80% of the time, if you see this specific shape that is broad and kind of strong, it's not super strong, but I would say it's like medium strong, right? A medium strong broad signal that starts from 3,000 to 3,500, it is 80% of the time always an alcohol. And notice here, right next to it, you have the characteristic CH stalagmites. Right here in the green. Remember, this is always going to show up in all of your spectra. This tells you nothing. This tells you nothing. It tells me that this is all you know, and you don't get points for that. This tells you nothing. This does not help us. Obviously, there's a CH stretch because it is a hydrocarbon. It is an organic molecule. But what else can you see? You see the OH broad, medium, strong signal between 3,000. Well, I should use another color to avoid confusion. I should use red. Between 3,000 and 3,500 wave numbers. And then that would be centimeters to the -1, or I can just use that, wave numbers. And again, you have a Gaussian distribution because sometimes some OHs are bonded to another oxygen, hydrogen bonding, and some of them are not. So you just get like a distribution of energies. And so you have a range from 3,000 to 3,500. But that is so characteristic of an alcohol, I don't know what else to say about it. Like if you see that signal right there, that's 100%, no, 85%, 80% an alcohol for sure. You'll notice there's like a CO stretch right here. Um, I mean, it would be enough because obviously if you have an alcohol, by definition, there's a carbon that is bonded to that oxygen. But we also see that stretch right there, the carbon oxygen stretch. This part right here shows up as a peak. It's a very sharp medium peak at around 1100. And you'll see that esters also show up around that. So carbon oxygen single bonds tend to show up around 1100, 1200 as a sharp medium peak. And then notice that at 1700 right here, 1700, notice there is no very strong sharp peak. So there is no carbonyl. The carbonyl will show up as this giant peak if it was present, but it is not there. So therefore, there are no carbon double bonded oxygens here, right? There's only OH because you can see this shape right there. It's so characteristic. Any questions about alcohols and phenols? And of course, with phenols, you have that carbon double bond carbon, so you would observe sharp peaks in the 1500s like we did earlier. So that's probably what this is, but it tells us right here that it is not a phenol, so we cannot claim that, right? You never go into this blind. You always have some idea what your molecule is. You cannot ever tell me the whole identity of the whole molecule just looking at an IR spectra. It is not possible. Any questions about alcohols? Okay. So let's look at an example. A special type of alcohol. Remember, there's components of functional groups and there's the whole functional groups. Carboxylic acids, by definition, contain a ketone, in other words, a carbonyl, and a hydroxyl. It is a compound group. It is a ketone or a carbonyl plus a hydroxyl. So when you have a carboxylic acid, you're going to see both. You're going to see the carbonyl peak at 1700. You can see it right here already. Right there. This is your carbonyl, carbon double bond oxygen. This is only your carbonyl. You have to tell me. You have to say carbonyl from carboxylic acid. If you don't say that, you're not being specific. You are not correct. You can't point to this and tell me this is a carboxylic acid. Which is it? Is it the carbonyl or the hydroxide? That tells me you don't know. You're not going to get the points. You have to be specific. I think this is a carboxylic acid, and here's the carbonyl of the carboxylic acid, and here's the hydroxide of the carboxylic acid. That's how you have to say it. And you'll notice once again, if you look at the OH, you once again have this very broad peak. You see that? That's again hydrogen bonding. But the peak is so broad, it actually blends in with the CH stretches. So these right here, this is your CH stretches right there. That looks like an E. Hold on. Yeah, I'm just gonna draw it like this. CH. You see that? Those would be your stalagmites. But the signal of the carboxylic acid hydroxide is so broad that it blends in. So what it does, it creates this compound signal that looks like a beard. We call this the wizard's beard. So the wizard's beard. And this is very iconic of carboxylic acids. If you see between 2500 and 3500, notice also it's very broad. It's from 2500 to 3500. If you see the wizard's beard between those two numbers, you 95% of the time have a carboxylic acid. The wizard's beard is very characteristic of the carboxylic acid. You can further confirm by looking for the carbonyl, right? You can say, well, look, I have my carbonyl, and then I have my OH beard. So of course I have a carboxylic acid. It should make sense. And again, I want to point out, what about the fingerprint region? What about everything else? What's this? I don't know and I don't care. What is this? I don't know and I don't care. What is this? Guess what? I don't know and I don't care. What about this? Bruh. As long as I see an OH broad signal, as long as I see the CH stalactite that creates the wizard's beard, and I confirm it by looking for my carbonyl, I know that I have a carboxylic acid. Everything else is just there. It's extra information. We only care about the two peaks. And so again, don't panic when you see this and start freaking out because of all the peaks. Don't start randomly guessing. If you know to look for the beard and the carbonyl, you know you have a carboxylic acid. It's that simple. And you know this characteristic stretches, right? Again, from 2500 to 3500, wizard's beard, and carbonyls are always around 1700. So any questions about carboxylic acids? And again, if you don't know your functional groups, if I tell you draw a carboxylic acid and you don't draw COOH, I mean, you can't even get this question right. You need to know your functional groups by this point. Okay, moving on to the next slide. I didn't clear the drawings. Here we go. Alrighty, ethers. An ether is a carbon bonded to an oxygen, bonded to another carbon. So it looks like this: carbon, oxygen, carbon. And this could be, I don't know, anything, you know. Usually we label this R, but it's just carbon, oxygen, carbon. And so if you only have an ether, again, you only have CH and you have two CO bonds, your spectra would look very clean. So in this case, dibutyl ether, well, that's four, right? So that would be 1, 2, 3, 4. Oxygen, 1, 2, 3, 4. So this is dibutyl ether. Well, you have CH, right? CH stretching right here, CH. That is right there. Again, very characteristic, useless, doesn't tell us anything, just that the compound is for sure organic. That's always there in all organic compounds. That you don't get points for pointing that out. That's obvious. That's always there. So what else is left? Well, the actual carbon-oxygen bond, this right here, the carbon-oxygen bond. And there's two of them, right? So you're gonna see that it looks like a carbonyl, but notice it's not as strong as a carbonyl. And notice that it's at around 1100. Plus minus, right? Sometimes it's at 1200, sometimes it's at 1000. In general, it's at 1100. So ethers, single, strong peak at 1100. Nothing else. Because what else is there? What about those two peaks at 1400? I don't know, man. That could be some sort of bending or wagging or something. The characteristic carbon-oxygen stretch is right here. Strong peak at 1100. So any questions about that one? Okay. Clear drawings. Move on to the next one. So again, esters. Esters are carbonyls and ethers combined together. So here's an ester, just to give you an example. You see the structure, you have the carbon, double bond oxygen, oxygen with whatever is there, and this could just be whatever, right? So you have a carbonyl and you have an ether. So you should see both of their signals. And sure enough, I'm going to use the color green. At 1700 or so, you have your carbonyl, carbon double bond oxygen right there. Very strong, sharp peak. And I just told you guys that at around 1100, we should see a strong carbon oxygen single bond. In this case, it moves up a little bit. It is at 1200, but notice it is the strongest out of the whole group. That's how you know it's that specific one. And that's it. There's no other peaks I can look at to confirm this is an ester. You know, once again, what's this? What's this? What's this? I don't know, man. I just know that I see my carbonyl and I know that I see my carbon oxygen single bond. And once again, notice that the stalactites are always present and they are not useful and you do not get points for pointing them out, They are always there. So that's how you tell the difference. What about aromatic esters? Well, again, when you have an aromatic system, the stalactites are not as intense. So notice once again, the stalactites are still here, but now they're actually useful. They're a little more specific. Look at that peak. That is an aromatic. This would be the CH3 stretch of a conjugated system. sp2 CH stretch right over here. That's this right here. That's this carbon hydrogen vibration. because now it's a little stronger because it's not a single bond anymore. It's a double bond or a bond and a half. So you do see some of it. But in general, you can get more information from looking at the rest of the spectra. So again, look at 1700 right here. You have your carbonyl. And look at around 1200. You can pick either this one or you can pick either that one. They're the two strongest ones, right? Some people might pick this one. Well, what's wrong with this? You're at 700, bro. That's a fingerprint region. We don't look at the fingerprint region unless we have no hope. So don't label this one. And then between 1400 and 1600 or at 1500-ish, you see the aromatic carbon-carbon double bond peaks. Very, very sharp peaks. But again, you know what your structure looks like before you go in there. So you use that to help you pick the peaks. You don't just randomly pick a peak and say, I hope this one is the carbonyl. I hope this one is. No, you should have some idea. But yeah, adding an aromatic conjugated system makes things a little interesting. But in general, the signals are still pretty characteristic and they are still present. So are there any questions so far? Is all of this making sense? Like we talked about how they vibrate at a specific frequency. Now we're measuring those frequencies. They each have different polarities, so they each behave differently. We have to look at the wave number, the intensity, and the shape of the signals. Okay. Next slide. Amines. You're 100% gonna get questions about amines. It's impossible not to because this is another very characteristic signal right here. And this one's cool because it actually gives you very useful information. You can tell me if there's two hydrogen-nitrogen bonds or just one based on the number of peaks. So again, I'm going to start off by ignoring the stalagmites right here. These don't tell me anything, just that there is a carbon-hydrogen stretch, and that is true for all molecules. Does not tell me any useful information. However, the NH stretch is going to show up to the left at a higher wave number than carbon, because nitrogen is more polar than carbon, more electronegative than carbon. So that's going to show up at a stronger wave number, larger wave number. If there is only one nitrogen and a hydrogen, there is only one peak. And therefore, this is a secondary amine. You only have one nitrogen hydrogen, the rest must be nitrogen carbon. If it is a secondary amine, sorry, a primary amine, I got it backwards. If it's a primary amine, meaning you only are connected to one carbon, you're going to have two NHs, and each one of those NHs is going to give you a unique signal. So if you're expecting your compound to be an amine, you can tell if there is an NH or an NH2 from IR. One of the rare cases where you get a lot more info than just what kind of functional group it is. And of course, a tertiary amine, that would just be nitrogen with a carbon, with a carbon, with a carbon. There's no nitrogen-hydrogen bonds, so there's no signals between 3000 and 3500 because there's no NH. Nitrogen-carbon is not as polar as nitrogen-hydrogen. That's why it's not as strong. That's why it doesn't show up at a high wave number. So in one of the spectra that you will receive for your quiz next week, you will have to see whether or not it is a primary or a secondary amine by looking at that weak peak from 3200 onwards. The number of peaks tells you the number of hydrogens. Does that make sense? And if it's an amide, those peaks are not there because there is no NH at all. That would be present a lot lower. Okay, next slide. This is where you guys start to talk. So we're all as a class gonna start going through this and we're gonna see what functional groups are present here. So you guys tell me now. I've talked enough. What functional groups do you see here based on the information we've learned today?
Is there an alcohol group in the wizard's beard?
Yes, yes, you have correctly identified the wizard's beard, right? And you said it was an alcohol, which is correct. There is an alcohol that looks like the wizard's beard present So this is OH right here. And you can see, you can draw like, I'm not the best artist, so I'm just gonna draw like a little face. And there's his beard right here, and he has like the wizard's hat up here, right? Yeah, this is the wizard's beard right here. And this alcohol from the wizard's beard is part of what functional group? You have to tell me the whole sentence.
The carboxylic acid.
Exactly. This is a hydroxyl or an alcohol from a carboxylic acid. How do you know? Look, you also start at 2500. You see right here, 2500, and you end at 3500. If it has a range of 1000, characteristically, it is a carboxylic acid alcohol, wizard's beard. What else gives you the final confirmation that you have a carboxylic acid? What else? You show me there's an OH, but what gives me the for sure confirmation that there's a carboxylic acid here?
The carbonyl at 1700.
Exactly. The carbonyl at 1700, very strong, sharp peak. This is your carbon double bond oxygen. And so if I put that together, I have carbon double bond oxygen and I have OH. Look at that. That is a carboxylic acid, right? So whatever this compound is, there is a carboxylic acid in it. I don't know if it has 5 carbons, 20 carbons, a million carbons. I don't know if it's, benzoic acid or acetic acid or ethanoic acid. I just know there's a carboxylic acid in here. I don't know anything else. Make sense? And that's how you do it. This is how you do it. So let's look at the next one. What about here? What functional groups are present here? Oh, I skipped. Here you go. What functional groups are present in this one? And we're here to learn, so don't be scared of guessing. Nobody learns IR in 3 hours. It takes a lot of practice, and we're practicing right now. And this is the only IR lecture you get. So after this, you're on your own. So please, any questions you have, now's the time. What functional groups are present here?
Is there an OH group?
There is an
The
OH group.
hydroxyl?
Where is it?
The very left.
Be specific with the number. Read the x-axis.
At 3400.
Excellent. Thank you. Yes. At 3400 wave numbers, there is an OH broad, medium, strong stretch. So this right here is OH. And notice it doesn't look like the beard, right? Because the beard would be caused by an overlap. Notice it doesn't start at 2500. It starts at 3200 and it only goes up to 3500. The range is much narrower. It does not look like a beard. The signal is medium strong, more medium than strong, I would say. It's broad. That is characteristic of OH. Is there anything else? Not that I can observe from here. I mean, it looks like there's this peak right there. That might be a carbon double bond carbon, but we can't be sure unless we have a structure. So I'm not gonna guess that. That could also just be some noise. I'm gonna just simply say for sure I have an alcohol. What's this one right here? What's this at 2900, 3000? What is this?
Is that a CH single bond?
That is a carbon hydrogen single bond. Yeah. And that is always present in all organic molecules. So you should know that it's there. You can identify it, but you won't be given credit for it because that's everywhere. You need to tell me what else you see. Okay. Awesome. But do point it out. I'm not saying don't think about it. Point it out. Because if that's the only thing you see, then you don't have any functional groups, right? By definition, you don't have any functional groups. So, all right, let's move on to the next one. Clear all drawings. And next. Okay. What about here? What are my functional groups? What do you guys see? Any carbonyls? Are there any carbonyls? Any carbon double bond oxygens? Any alcohols? Any ethers? Can't move on until I get some answers. Anyone?
Is it an amine?
It is an amine. What type?
Primary?
Primary amine, right? How do you know it's primary?
It has the two peaks.
And those are what kind of peaks?
Um, they're they're like broad and they aren't as intense, right?
Yep, not very intense. So we can call that like medium, right? And then they're broad, like they're relatively broad, right? They span a while. You see that right there? But more importantly, you see the two peaks right here. And you said that those tell you that it is a primary amine. What does that mean? It means that these are your nitrogen hydrogen bonds. There's two of them. Everything else is just a carbon. So yes, you are correct. Those are amine peaks. You can find them between 3200 and 3500. If there's one of them, NH. NH, if there's two of them, it's NH2. Yes. The peaks are strictly NH stretches. What's this at 3000? What's this at 30, at 2800? What's all this?
The CH bond.
Those are the CH stretches, right? They're always there. You should be aware that they exist. So once again, at around 1500, 1600, we see these sharp peaks. That makes me suspect that there's probably a carbon double bond here, but I'm not quite sure. So I don't want to make that claim. But if we had a formula, we could definitely make better statements about this. But all we can say for sure is that the nitrogen hydrogen bond is present. It is a primary amine. Make sense? All right. So once again, clear the drawings. And next slide. What about this one? What is this one right here?
Is it another amine?
It is. What type?
The secondary?
It's secondary now, right? Exactly. So once again, right, look at the region. Remember, we look for wave numbers, we look for shape, and we look for intensity. So here, the wave numbers are still the same, 3200 to 3500, roughly. And now we're only seeing this single peak, so that is an NH stretch, and the rest is just carbon, nitrogen stretches. You see that? And actually, those carbon nitrogens, the NR, the N carbon, that one is probably this one right here. This is probably your nitrogen carbon stretch or bend. How do you know? Well, remember that for carbon oxygen, remember carbon oxygen single bond? That one is usually found around 1100. Well, in the periodic table, you have carbon, nitrogen, oxygen, and fluorine. So carbon oxygen That would be 1100. Carbon nitrogen would be a little bit lower than that. Maybe 1000, maybe 900, maybe 1100 as well. And so you see there's a very strong peak. That must be your carbon nitrogen bond right there. Is it a bend? Is it a stretch? I want to say it's a stretch, but I'm not really sure. So as long as you tell me that that's carbon nitrogen, that should be good. You see? And so you can make predictions too, just based on the polarities of other functional groups as well. What's this at 3000 in the pink? What's this?
The CH bond stretching.
Those are the CH bond stretches, right? Yep. Every time I'm going to ask you because those are always there and you should not confuse them with anything else. Okay, any questions about this one? Alrighty, next slide. Here's another one, right? This is where I'll be like, oh, let's do unknowns. Same thing, right? All of these are unknowns. We don't know what they are. What do you see here? What are the functional groups potentially here?
Is it an alcohol?
It is an alcohol. How do you know?
The OH bond at like 3600?
Mm-hmm. Yep, the OH bond is over here. It is very polar. It has hydrogen bonding, so it's very broad. And it is, I would say medium strong. I would call this medium strong broad peak. So medium strong broad peak. And usually those are above 3000. I would say this one starts at around, 3200 and it goes to around 3500. So yes, definitely an alcohol peak. Once again, these are your carbon hydrogen stretches. Specifically, we say sp3ch stretch. There's no carbonyls at 1700, so there's nothing else. Again, we see this peak here. There might be a carbon-carbon double bond. I'm not really sure, so I cannot make that claim, but I suspect there might be something there. And this peak, I mean, I don't know. That could just be the carbon-oxygen stretch from the alcohol right there. This could be your carbon-oxygen stretch right there. Anything else? We don't really know. We cannot make any more claims. Does that make sense? All right. Let's look at the next one. What about this one? What functional groups do we see here? Do we see alcohols? Do we see carbonyls? Do we see amines? Do we see esters, ethers? What do we see? It's gonna be on your test, so you gotta ask yourself these questions. Well, let's see what we don't see, right? Do we see a carbonyl at 1700? No, right? There's no giant carbonyl peak that would look something like this at 1700. So there's no carbonyls. Do we see alcohols? Do we see an alcohol signal here? We don't. So there's no alcohols. Do we see a wizard's beard from 2500 to 3500 that would look something like this? Do we see that? We also don't see that. So there is no carboxylic acid. Do we see a carbon oxygen ester or ether bond here? Like a very strong but not as intense signal, maybe like that? We also don't see that. So we're not really seeing anything, right? So what is most likely this molecule?
I'm gonna say a hydrocarbon.
It's a hydrocarbon, right? Now, is it an alkane? Is it an alkene? Or is it an alkyne?
And is it an alkene?
Why is it an alkene? You're correct.
Because it has the second, like a second small peak
Mhm.
before the larger peak, but it's closer to the larger peak.
Can you give me the number specifically? There's a lot of peaks.
Um, the smaller peak at about
Yes.
3100.
Yes. Thank you. Yes. This peak right here, we would call that a weak, sharp peak. This one is at 3100. This is typical of an sp2 carbon hydrogen stretch. Very sharp, very weak, always higher wave number than the typical CH stretches. And actually, since we know it's an alkene now, some sort of double bond is present, we can actually make more assumptions now. We can actually start assigning more peaks. So I'll give you guys a hint. This one is significant. What is this peak? For once, the stalagmites are not simply just stalactites. Remember, there's a double bond in it now, so it could potentially be what type of molecule? It could be a chain, or it could be anyone.
Is it a ring?
It's a ring, right? It's an aromatic ring, right? Specifically, double bond, single bond, double bond, single bond. This is a really bad benzene. Sorry about that. But yeah, it is a aromatic ring. Specifically, this is the aromatic hydrogen, carbon hydrogen aromatic stretch. Very sharp, medium strong at around 3000. You can only know this is there if you first observe the alkene peak right there. If you don't see the alkene peak, it's going to be difficult for you to say this is aromatic. And you can further confirm that there's a ring because you also see this very sharp thing at around 1500, a little bit higher. So this is what I've been kind of unsure of earlier. I guess for sure now there was no carbon-carbon double bonds. But now that you know you have a double bond here at 3100, now that you see there's an aromatic hydrogen signal at 2900, well, for sure you can tell me this is the carbon-carbon double bond stretch right there. And also you see these little like bands at the top, like that's very typical of aromatic compounds. So this might be something like, I don't know, toluene or some sort of like chain, to infinity, whatever. We don't know how big the molecule actually is. We just know there's a ring, it's aromatic, and it has double bonds at some point. Make sense? So yeah. So this is what I'm telling you. You need to know where your carbon hydrogens are. Just because you don't see any other functional groups doesn't mean they're useless. They could still give you some information. Sometimes you'll see the standard stalactites and you'll say, well, it looks like there's nothing here. This just has to be a plain old boring alkane. Of course, that's all it can be. If that's what your mind tells you, that's all it can be. Any questions about this one? These are a bit trickier, but you can still see based on the lack of other signals. So if you also don't know the other signals, you cannot make assumptions about just a hydrocarbon. Alrighty. And unknown number 3, what do we see here? What functional groups are present here? Bugs Bunny.
There's a carbonyl.
There's a carbonyl. Where's it at?
It's at 1700.
17, 1710, 1720. I don't know, right?
Yeah.
It's a carbonyl. And you can just say roughly 1700 inverse centimeters or just 1700 wave numbers. Okay. What type of carbonyl? Is it a ketone carbonyl? Is it a carboxylic acid carbonyl? Is it an ester carbonyl? You can tell me based on this graph. So I'll give you the first hint. If this was a carboxylic acid carbonyl, what else would you observe?
OH.
You would observe an OH and it would look like a beard, right? And it would be from 2500 to 3500. Is that what you see in this graph? There is no wizard's beard between 2500 and 3500. So there cannot be a carboxylic acid. So this is not a carboxylic acid carbonyl. So what type of carbonyl is it? Is it an ester carbonyl? Well, if it was an ester carbonyl, you would see a peak of similar shape and size at 1100. Is that what we see? Well, we see this peak, but this is very sharp. We say VS, very sharp medium peak, and it is at 1200. That's not a carbon oxygen peak. A carbon oxygen peak would look more like the carbonyl peak, and it would be at around a similar height. So I'm going to say this is not a carbon oxygen ester. So it is not a carboxylic acid. It is not an ester carbonyl. So what else could it be? And this is where your functional groups come into play. Is it an amide? Well, if it was an amide, we might see something over here, right? If it was primary or secondary, but we don't see anything. So there is no carbon, double bond oxygen, carbon, nitrogen. There's none of this, right? So it's not an amide. So what else could it be? I mean, it might be just a ketone by itself, right? It might just be carbonyl, R, and R. It could be. What else could it be? I'm missing one functional group I haven't mentioned that contains a carbonyl. What is this called? Somebody tell me. What is that called?
An aldehyde.
It's an aldehyde, right? I did not talk about the aldehyde. Well, the aldehyde, it was one of the first examples we saw. This carbon hydrogen stretch, remember, carbon hydrogen stretches are roughly found at 3000. That one is this one right here. It is, I don't know, it kind of looks like a lobe of some sort, just chilling there. It's always at the lower wave number of the stalagmites, and it's not very strong. Sometimes you don't see it. Sometimes you do have an aldehyde, and you don't see it because the other signals are interfering with it, or it blends into the whole thing. In this case, you can't see it. It's very characteristic. So that is an aldehyde CH stretch. So that peak plus my carbonyl peak confirms to me that this is an aldehyde. Make sense? So it's a puzzle. It's another puzzle. Organic chemistry is just one giant puzzle. You have to be able to piece things together and reason your way through it. And you're like, well, if I had a carboxylic acid, I would see a beard. If I had an ester, I would see a peak. If I had an amide, I might see some NH bands. If I had just a ketone, well, I mean, I would only have this and nothing else. Yeah, work through it. Talk your way through it. Think your way through it. So this would be definitely an aldehyde carbonyl. Okay, next one. What's this one here? One of the hints is that this is a very, very clean spectrum. There is not a lot of peaks. There's no carbonyl peaks. There's no alcohol peaks. There's no carboxylic acid peaks. There's no CH2 peaks. There is no CC peaks. What do you see? What is the only peaks that we really observe? There are peaks. Which ones are they? What are these right here? But you gotta tell me what they are. Stalagmites. What are the stalagmites?
Is it an alkane?
It is just an alkane. This is your CHSP3 stretch. There's nothing here. There's nothing here. And you're like, what is this? I don't know. That's probably a carbon hydrogen bend somewhere. Maybe this one too. Maybe all of these. We don't see anything else. If it was a carboxylic acid, we might see an alcohol. If it was, we might see a carbonyl. If it was an amine, we might see NH. We might see carbon oxygen at 1100. We don't see anything. We don't see sp2 very sharp peak. We don't see sp very sharp peak. We don't see at 1600, we don't see like very sharp aromatic peaks. Some people would be like, well, this looks like the aldehyde you just talked about. But an aldehyde has a carbonyl. So you would also see something at 1700. So you can't just be like, oh, it looks like the previous one. So there must be a carbonyl hydrogen. No, because there is nothing at 1700 that's very strong. There's nothing in here, in fact. This is strictly just an alkane. Make sense? Alrighty. So moving on to the next slide. Number 5. Which one is this one? What is this functional group here?
Is it another primary amine?
Excelente. It's another primary amine. Why? Because amines are usually found between 3200 and 3500. They are not very strong, and you can see whether there's one or two peaks in that region. Since you see two of those, this must be the nitrogen hydrogens stretching right there. At 3000, this is just your carbon hydrogen. What are these? I don't know, man. This could be anything else. Probably one of these is like a carbon nitrogen bend of some sort. I don't know for sure. We can't make claims. All I know is that I see my characteristic amine NH stretches, and then this is primary amine. So primary amine. So you guys kind of hopefully see by now like what we do, right? We have the whole graph. We don't look at the whole thing. We look for specific things. The absence of things usually tells us it's just a boring old alkane. Okay. Clear drawings. Unknown number 6. Sometimes you'll get a spectra that looks really funky. So notice here the baseline is at like 50%, right? Whoever used this didn't clean their instrument or didn't calibrate it properly. Regardless, we still have some information. Just like, sometimes you do a TLC plate and you don't get the spots perfectly small, but you can still get some information out of it. This is one of those spectra where it looks a little funky, but we can get a lot of information out of it. So, what is the functional group here?
Is is that like a wizard's beard? So then there would be that's the OH, so then it would be a carboxylic acid?
Exactly. Yes, yes. So even though the resolution of this spectra is not as good, you can still see just based on the range, right? 2500 to 3500, you have a very broad signal. It overlaps with your stalactites, very broad. And you also have this at 1700. What is that? This is your carbonyl. If you have a carbonyl and you have a very broad signal from 2500 to 3500 that overlaps with your stalactites, that would be your OH. If you put them together, carbonyl plus hydroxide gives you carboxylic acid. Yes, this is a carboxylic acid. And then this carbon oxygen stretch is at 1100. So if you go to like 1100, you see that that is your carbon oxygen stretch right there. Does that make sense? So yeah, in this case, the spectra is not the best looking, but you still got to be able to read them even if they're not the best. See, you can just imagine that the baseline starts here and just pretend that you're looking at it. It's relative, right? That's what I'm saying. You have to look more at the shape, more at where they are. How do they look like? Not exactly, oh, well, I didn't know it was a carbonyl because it was at 1850. Maybe the instrument is off. If you know what a carbonyl signal looks like, you should be able to reasonably guess that it's a carbonyl, even if the spectra is not the best looking spectra. Okay? Let's see, clear all drawings. And so, yep, we summarize all of that information in a table like this. You will most likely get something like this for your exams and for your quizzes. And again, notice that the wording, right? You have that little squiggly mu, that is wave number. It tells you the bond type. It tells you the hybridization. So if you're still struggling with sp, sp2, you really need to get that down so you can tell me if it's a single, double, triple bond. It tells you where they are. It describes them as strong, broad, medium. Other tables have different, more words to describe them. You can take a whole class on IR spectroscopy if you're really interested in it in your upper divisions. But in short, this is the summary of that information. And that is pretty much the end of our slideshow. So I will show you one final thing, and then after that, we will be heading out. But in the meantime, are there any questions so far? Any questions about anything that we covered, anything of the sort? Now's the time to ask. Alrighty. Well, for practice, since the book doesn't really have a lot, and you guys kind of have to go through the module 4 on your own, um, I recommend you go to this website. It is the Spectral Database for Organic Compounds, SDBS. It's a highly kept secret unless you take like the real OChem. And even people who take real OChem never learn about this until they're in grad school. So my professor was able to teach me about this a long time ago. You go ahead and click the disclaimer. You can look up any compound and get the IR spectra. So warning, I will be using this database to find spectra for your post-lab quiz. So I'm gonna come in here and find some spectra of some common compounds like acetone, blah, blah, blah. And I will post that spectra in the quiz, and then you have to tell me what are the stretches and what functional groups they correspond to. So for example, I'm gonna type in acetone. I'm gonna click search, and you're gonna see I'm gonna get this list. The very first result, compound name acetone, you see we have an MS, a CNMR, HNMR. That's all sorts of spectroscopy. I'm going to click where it says Y under IR. That means yes, the IR is available. And it's going to give me the IR spectrum. You see that? And so you can see it gives you the structure and it gives you the spectra. This is a real spectra that somebody recorded and submitted. So this is considered accepted. This is considered as a reference. You see right away, we have our carbonyl compound, right? It's acetone, so it does have a ketone. You see right away, we have our carbonyl compound right there. You see, this is a carbon double bond oxygen. You see that? So use this. Use these to practice. Look up compounds that you're interested in. Disclaimer, if you look up drugs, they're not going to show up. I've already tried. You can't find drug compounds on this website. They were very careful about that because then you could help the criminals confirm if they actually made up your compound, right? So You do want to be careful. You're searching for molecules that are not illicit. So for example, maybe I want to look at benzoic acid. And then I'm going to go and click search. And again, you see here, benzoic acid, result number 2. They do have an IR spectra, so I'm going to click it. And then look at that. And you see the wizard's beard right away, right? Look at that. It's a very broad signal from 2500 to 3500, and it looks like a sort of very short wizard's beard. Look at the very strong carbonyl peak at 1700. And look at the structure. It's a carboxylic acid. So this is good if you want to look up your own compounds and just look at the spectra and kind of see. I am going to pick a spectra from this database. I'm not going to tell you what compound, obviously, because you have to tell me. But this is some good way to get some practice and also just learn, practice your nomenclature, practice your structures, practice your IR skills. Everything is here. I'm going to do one more. Let's do acetaminophen. You can just click search. And then you see it's the only result, and it has the IUPAC name. So again, good time to practice your nomenclature. I'm going to click Y. And there's acetaminophen right there, you see? And you have your carbonyl at 1700. You have a carbon-nitrogen stretch at around 1200, 1250. You have a single nitrogen-hydrogen stretch at around 3400. This time it looks like a sharp peak rather than a little weak signal. That is because that aromatic ring introduces new stuff into it. So you can definitely see that the amine is still there, even though it doesn't look like the examples. And that's something else too. Sometimes the examples are very simple, but when you have a more complicated molecule, the signal is still in the same region, but it doesn't look exactly like the examples we gave you. So that's why it's a good idea to go through this on your own. All right. So this is the spectral database for organic compounds, the Japanese spectral database for organic compounds, .go.jp. All right. I'm going to stop sharing now. And this concludes the lecture for IR spectroscopy. So thank you very much for your attention and your patience today. So the post-lab quiz will be given in 2 weeks, I believe. It is at the second day of lab 5 that you guys will get your post-lab quiz. And we'll do it at the beginning of class. So next week for lab 5, there will be a pre-lab quiz. And for day 2 of lab 5, there will be the post-lab quiz at the beginning for IR. The worksheet for this one, you can find that in the course packet. That one is also due at the end of day 2 of lab 5. So everything is due in 2 weeks. The worksheet is due in 2 weeks. You took the pre-lab quiz this morning. The post-lab quiz is in 2 weeks as well. Next week, we'll be starting with lab 5. We are meeting in person again, so please show up, be on time. Other than that, if you have no more questions, you are free to go. I will stick around if you have any more questions, and I will press stop to the recording right now. So thank you very much for attending. Really appreciate it. I hope you have a great weekend, and I will see you guys next Thursday.